Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting concept in the subject analog and digital communication. We're going to see noise performance in DSB-SC system, right? We're going to see how noise affects the DSB-SC system, and we're going to calculate the SNR and figure of merit for DSB-SC system, right? Before going in depth about this particular question, this is going to be a very important topic in this particular subject and very important question where it can be asked in part C around 15 marks, right? And this particular video, we're going to see the complete derivation of noise performance in DSB-SC system. And believe me, students, this derivation is going to be very simple, right, when compared to the other books or other videos, right? I'll explain you very clearly how to calculate the noise performance in DSB-SC system. And if you can understand this particular concept, we can derive the noise performance of SSB-SC system in the same pattern, right? So before going in that, first you got to understand what is SNR and what is figure of merit, right? And already you know what is noise, right? So noise in AM system, whenever you transmit any particular signal, right? If you're going to transmit any particular message signal from a transmitter to a receiver, definitely noise will get added to that particular message signal, right? And at the receiver, we have to overcome that particular noise and we have to detect that particular original message signal, right? That is the normal communication process, correct? Now we will see how this noise is affecting the AM system and how much that the DSB-SC system is getting affected because of that noise, right? And to understand that, you have to know two important parameters. One is signal to noise ratio and figure of merit, SNR and FOM. Signal to noise ratio. Signal to noise ratio tells you how good the signal is, right? That is, it tells you how much amount of noise is present in the signal, right? From the name you will understand S by N, signal to noise ratio, right? The amount of noise that is present in the signal power, right? So here, if the SNR is high, then which means the signal power is good, right? The noise is very less. If the noise becomes high, then the SNR will become very low, which means that it will degrade the performance of the system, right? So signal to noise ratio tells you about the power of the signal, right? How good the signal power is. And what is figure of merit? Figure of merit tells you how well the complete system, complete DSB-SC system or an SSB-SC system, how it handles the SNR, right? How it maintains the SNR. That is, figure of merit can be defined as SNR output divided by SNR input, which means how well the system maintains a constant SNR, right? How well a system maintains the SNR. That is called as figure of merit, right? So now we will see how the noise is affecting the AM system, and there is some important properties where in AM system where we know that whenever we transmit any particular signal through a transmitter, right? Obviously that the signal which we transmit is a modulated signal, and that signal will be transmitted to the channel, right? And this channel, while transmitting the message signal through the channel, definitely noise will get added, right? Noise is getting added to the original message signal, so it can be called as additive noise. It can be called as additive noise, right? And when this particular signal, now here you are transmitting only the message signal, but here while the receiver receives the message signal M of t and N of t, which means it has message and as well as the noise. And the receiver now, it has to overcome this noise and it has to demodulate the original message signal, right? And for that, it has band pass filter. That is, it will select the exact signal, right? That is, it will band limit the particular signal, right? Whatever signal, say for example, we are using DSB-SC signal. So this will be tuned in such a way that it will receive that DSB-SC band, right? And it will band limit some sort of a noise. That some sort of noise will be eliminated here itself, and then it is sent to the detector, where detector will demodulate the original message signal, and we will obtain the original message signal, right? And here, if you take noise, the noise at this particular end, before the receiver, it will be very high, but before the detector, it will be, that is, at the output of the output noise will be lesser because it is filtered and it is detected, right? So the noise, there will be a variation with this input noise and as well as the output noise. Clear? Right. So now with this, we will derive the signal to noise ratio and as well as figure of merit for DSB-SC system, right? And before seeing how it affects the DSB-SC system, you know that SNR is nothing but signal to noise ratio. Signal to noise ratio, which means we have to calculate the signal power to the noise power, right? We have to know, we have to find out signal power and also noise power, and if we divide, we will be able to calculate the SNR, right? And to find out the figure of merit is a very important parameter that evaluates the noise characteristics of the modulation system. And as I said before, figure of merit can be represented as SNR output divided by SNR input, which means we have to calculate the SNR output and then we have to calculate the SNR input, right? And then we have to divide so that we will obtain figure of merit, right? So to find out the SNR output, what we have to do? We have to find out signal power at the output, noise power at the output. Similarly, to find out the SNR at the input side, we need to calculate signal power at the input and noise power at the input. Only if we calculate all these parameters, we can able to determine the figure of merit, right? So your overall derivation is going to be, you're going to derive the SNR output and SNR input, right? That is, you're going to determine signal power at the output, noise power at the output, similarly signal power at the input and noise power at the input. And by that, we can able to evaluate, you can able to calculate the figure of merit, right? Now we'll see, these are the very important information, assumptions that you need to follow to calculate the figure of merit, right? As I said, if you consider the original message signal as f of t, then definitely there will be a noise which is called as additive noise because it is getting added, right? And we consider this noise as a white noise. That's because the white noise will have a uniform power spectrum over the entire band, right? So the power spectral density can be given as eta divided by 2 into bandwidth, right? So this is the noise power spectral density, eta by 2 into bandwidth. So the total noise power can be obtained from this particular calculation. And I've already said that the noise before the detector, what you will do is you will use a band pass filter, right? And that band pass filter, what it will do is it will reject all other signal and it will send only the desired signal, right? And that signal, right, that particular signal, what it will do is it will allow only the narrow band signal, which means here you can see here the noise is getting added, right? And that signal will be band limited here, and it will be band limited, only a narrow band signal will be sent, right? And that power spectral density will be given as SNI is equal to eta divided by 2, right? That is the white noise at the input of the detector, right? That is given as eta by 2. And you can see, as I said, this is a white noise where it will have a uniform over the entire frequency band, right? The power spectrum will be uniform, that is eta divided by 2, right? So now how will you calculate the input noise power? We already said input noise power can be calculated using this one. That is, total noise power can be calculated into eta divided by 2 into bandwidth, right? So eta divided by 2 into bandwidth is nothing but 2 FM, because we are going to consider the SSB-SC, that is DSB-SC system. DSB-SC system, we know that DSB-SC system bandwidth is 2 FM. So the input noise power, you can see that the input noise power is eta into Fm. We have calculated. I have already said in order to calculate the figure of merit, you need to calculate signal power, noise power at the output and signal power, noise power at the input. Right. Now what we have calculated is we have calculated noise power at the input side. This is going to be common for all the noise in the AM system, that is a DSB-SC system or SSB-SC system. Right. Hope you understand till here. We have just assumed that it is an additive noise and we have considered that power spectral density is eta by 2, so that the total noise power is eta divided by 2 into bandwidth. So if it is bandwidth, we are going to use 2 FM, right? So if it is 2 FM, the input noise power is eta divided by 2 into 2 FM, so that we will obtain eta FM. This is the total noise power, input noise power, right? And now we will see the DSB-SC system, right? So DSB-SC system, already I have explained how DSB-SC signal is generated, right? And we have seen the various AM receivers as well, right? So this is the complete DSB-SC system. We can call this DSB system as synchronous detector, right? Or coherent detector, right? So why it is called as coherent detection, I'll tell you, right? So this is transmitter, this is the transmitter side, and this is the receiver side. This is the receiver side, right? So now the original message signal, we know that while how the DSB-SC signal is generated, right? The original message signal f of t, and that is multiplied with the carrier signal, right? And then that signal is sent as the DSB-SC signal, which is mentioned as f of t cos omega ct, right? Cos omega ct. This is the original DSB-SC signal, right? And now this signal is sent to the channel. So what happens here? The noise gets added. So understand this particular block diagram very clearly so that you can follow the derivation in the same way, right? So f of t cos omega ct is transmitted. That is DSB-SC signal. It is transmitted, right? And during transmission through the channel, the noise will get added, right? And at the receiving side, what will happen? Not only this particular DSB-SC signal, along with that, you will be having this additive noise as well. So it will be f of t cos omega ct plus n of t. This is the signal which is received at the receiver. But at the receiver, you will be having the band pass filter, which will allow only frequency that is tuned to this particular omega c, right? So part of the noise signal will be band limited here itself, right? So which means it will become a narrow band noise while transmitting this band pass filter, and then it is sent to the synchronous detector. And as I said before, this detector is called as coherent detection. This type is called as coherent detection or synchronous detection. That's because we are using a product modulator and we're going to use the carrier signal, right? That is, if you're going to regenerate the carrier signal at the receiving side, right? That is, whatever carrier signal that is used at the transmitting side, if you're going to use the same carrier signal at the receiving side, if you're going to regenerate the same carrier signal, then that particular detection is called as coherent detection, right? Or you can also put it in other words, that is detection which happens with the knowledge of the carrier signal, with the help of the carrier signal, then that is called as coherent detection, right? And if the detection happens without the knowledge of, without the need of carrier signal, then that is called as non-coherent detection. And here, this is called as coherent detection because we're going to use the same carrier signal, right? And now, along with this signal, what we are doing is we are multiplying a carrier signal. We are multiplying a carrier signal, correct? And that particular signal is sent to the low pass filter, and low pass filter will remove all high frequency signals and allow only the low frequency signal. And we know that that is because we need to reconstruct the original message signal. The original message signal is the low frequency signal, right? And from this signal, we can able to obtain the original signal that is transmitted, right? So this is the complete working of a normal DSB-SC system, right? And coming to the derivation, we were calculating the SNR and figure of merit, right? So far we have determined what is noise power. This is done. This is done. Now what we have to do, we have to find out signal power at the input, signal power at the output, noise power at the output. Correct? Now we will calculate the noise power at the output, right? So to calculate noise power, as I said, you can see here, this DSB-SC signal comes along with the noise, right? Now we are going to calculate only the noise. So I am representing this noise. This signal n of t can be represented as nc of t cos omega ct minus ns of t sin omega ct, which means this is in phase component and this is quadrature component. This noise signal will have two components. One is in phase component, another is quadrature component. We are calculating only the noise power, so I am assuming only that I am taking only the noise here, right? And we know that cos omega ct is multiplied along with this particular signal, correct? So that is here, you can see here what happens, n of t is multiplied with cos omega ct, right? You also have this particular signal, but I am just taking the noise signal because we are calculating the noise power. And if we're going to multiply the signal, n of t is this one, nc of t cos omega ct minus n of t sin omega ct, that is multiplied with this particular cos omega ct, where you will obtain this particular expression, cos square omega ct and sin omega ct cos omega ct, right? And we can apply the trigonometrical formula for this particular expression, right? This is the expression which we obtained. Instead of cos square omega ct, we can write it as this way, right? 1 by 2, 1 plus cos 2 omega ct. And similarly, instead of this one, we can write it as 1 by 2 sin 2 omega ct, right? And this equation will become like this, right? Because you're going to multiply this 1 by 2 nc of t, right? And then you will obtain this particular expression, correct? Right? This expression will be simplified in this form, right? And now what happens? This is the signal which we are sending it to the low pass filter, correct? So you can see the system, this is the signal. After multiplying, what you are doing, you are sending it to the low pass filter. Now what low pass filter will do, it will remove all the high frequency component. You can see these are the high frequency component. So that components will be rejected and only the low frequency component which is allowed, that is 1 by 2 nc of t, right? That is, this is the noise at the output. So if you understand here, this nc of t is nothing but the input noise power, and n naught of t is nothing but output noise power, which means the output noise power will be only half of the input noise power, right? So we can write it as n naught of t is equal to 1 by 2 nc of t, right? Clear? Right? Now this is what we have obtained. That is, we can also write it in this way, n naught of t, right, by nc of t is equal to 1 by 2. You can also write it in this way, correct? And now we have obtained the noise power, right? What is that? We have obtained the noise power is half of the input noise power. That is what we have obtained, correct? And from this, we can able to calculate the total output noise power, right? Total output noise power. How will you calculate total output noise power? That is, you can see here, we need to find out the power spectral density, right? Power spectral density, we know that power spectral density is the mean square value of the signal, right? What is mean square value of the signal? Mean square value of the signal is nothing but this is the signal, power, right? So now the mean square value will become 1 by 2 whole square, 1 by 2 of whole square, right? Where it becomes 1 by 4, right? So the power spectral density can be given as, that is, output power spectral density can be related to input power spectral density in such a way that mean square of the particular signal. So here it is 1 by 2, that is 1 by 4 into SNC of omega, that is power spectral density at the input power, and this is power spectral density at the output power, right? That is power spectral density of n of t, and this is power spectral density of nct, right? And we know that already power spectral density at the input power is eta, right? From the assumption, right? Eta. And if you're going to substitute this eta, then signal power will become, that is power spectral density of S and naught W will become eta divided by 4 around this particular frequency band. Correct? And now we know that output noise power, that is we have the formula. How will you calculate the noise power? That is power spectral density into the bandwidth. So what is power spectral density? Eta by 4. And we know bandwidth is 2 FM for DSB-SC. From this we can obtain N FM divided by 2. N FM divided by 2. Right? This is output noise power. This is output noise power. We have already calculated the input noise power, and this is output noise power. Right? And what is the input noise power we have calculated? We have already calculated input noise power, that is Ni is equal to eta into Fm. Correct? This is what we have seen in the assumption itself. Right? You can see this is what we have obtained. Right? So that is what I am recalling here. Right? So input noise power is equal to eta Fm. So now what is N naught? N naught is eta Fm divided by 2. Eta Fm divided by 2. Right? And what is Ni? Ni is eta Fm. Eta Fm. So now what happens? This eta Fm get cancelled and it will be 1 by 2. Correct? Right? And this is the ratio of noise power at the output to the noise power at the input. Right? N naught divided by Ni. Now we have obtained what is N naught Ni. Right? And now we are going to calculate the signal power. We need to find out S naught by Si in similar fashion. How will we calculate it? We know that how will it represent the DSB-SC signal, right? The DSB-SC signal is represented as f of t cos omega ct, right? How will you calculate the signal power? We know that power is equal to V square by R, right? And this will be related to RMS value, which is VRMS divided by root 2 whole square. So which means here is f of t. So it will be represented as f of t whole square, f of t divided by root 2 whole square, right? So which can be written as 1 by 2 f square of t. Clear? Right? And this is input signal power. And what will be the output signal power? Output signal power will be half of this particular signal, because right at the output, right, we will band limit the signal, right, it will be detected and we will be getting only half of the f of t signal. The amplitude will be half of the f of t signal. So if it is half of the signal, once again you have to calculate the signal power using mean square value, same like this way, right? So here for f of t we have obtained 1 by 2 f square of t, right, for f of t, normal f of t signal. Now if it is half f of t, then what will happen? It will be 1 by 4 into f square of t, the same way, right? Or you can also put it in this expression, right? So it is already, it's 1 by 2, right? So there will be 1 by 2 here, right? And this, because of this f of t, what will happen? F square of t, f of t whole square divided by root 2, right? And now what will happen? 1 by 4 into f square of t, right? And now we obtain, now we can write this 1 by 4 f square of t as 1 by 2 into Si, because this 1 by 2 Si, right, you can write it as 1 by 2 Si, correct? So it's 1 by 2 and remaining part is Si, that we can write it. So from this we can able to write it as S naught by Si is equal to 1 by 2. Right, now you can see here S naught by Si, that is ratio of signal output power to the signal input power is equal to 1 by 2, and similarly the noise power at the output and the input is 1 by 2, right? And the figure of merit will be equal to 1. How is that? I am going to determine that. We know that figure of merit is signal to noise ratio at the output to the input, right? So S naught divided by Si and N naught divided by Ni, right? And this can also be written in this way, right? You can see S naught divided by S naught divided by N naught and Si divided by Ni, right? So if you're going to reshuffle this, right, I can write it in this way, right? Ni divided by N naught, Ni divided by Si, right? So I can shuffle it in this way: Si divided by S naught divided by Si, Ni divided by N naught, right? And we know that what is this particular value, right? What is this particular value? It is 1 by 2, and also this is 1 by 2, right? And this gets cancelled, and that is 1. So you can see S naught divided by Si is 1 by 2, and N naught divided by Ni is 1 by 2, right? So what happens here? The figure of merit is equal to 1. This is the same figure of merit for AN system as well, right? So today what we have seen is we have seen the noise performance of DSB-SC system, and this is very, very important question. I believe this video is very useful for you. Thank you, my dear students.